two long, thin parallel wires, 13 centimeters apart, carry 35 amp currents in the same direction. We are to determine the magnetic field at the point which is 10 centimeters from one wire and 6 centimeters from the other wire, as shown in the figure. This problem, finding the magnetic field due to two line currents at some arbitrary location, bears a striking resemblance to the problem of finding the electric field due to two point charges at an arbitrary location. There are, however, two significant differences. First is the fact that if this red circle represents a line of current, the dot indicating that it is coming perpendicular to the screen and towards your eyes, we know that the magnetic field will wind up making circles around this current rather than lines that radiate away. As a result, when we decide upon the direction of the magnetic field at the point P due to each one of the two wires, we'll have to understand that this magnetic field would be located in a direction tangent to the circle that surrounds the wire's center. The second complexity is that the given information in the problem, 13 centimeter, 6 centimeter, and 10 centimeter, will require a little bit of geometry calculation before we're able to discern the angles involved for our field vectors and thereby be able to take components in a methodical manner. The solution here will be to use the law of cosines. We remember that the law of cosines relates the sides, which we will label as lowercase a, lowercase b, and lowercase c, to the angles that are opposite to each side. And in this notation, we're going to use uppercase A for the angle opposite to A, similarly for C, and similarly for B. The relationship, known as the law of cosines, tells us that A squared is B squared plus C squared minus 2BC times the cosine of the angle capital A. In our solution, we're going to label the top wire as wire 1, the bottom wire as wire 2, and these two angles, as indicated by the curved lines, as being theta 1 and theta 2. We'll need one application of the law of cosines to determine theta 1 and a second application of the law to determine theta 2. Let's begin with theta 1, where we recognize that the 10 centimeter side is the one that is opposite to theta 1. Therefore, the A parameter in our law of cosines is going to be the 10 centimeter, and B and C are going to be the 6 and 13 respectively. Filling in the three known sides, we notice that there is only a single unknown in this equation, and that is theta 1. We'll first solve for the cosine of theta 1, which yields the expression negative 10 squared minus 6 squared over 13 squared divided by twice 6 times 13. And the result of this is that the cosine of theta 1 is 0.6731, meaning that theta 1 itself is 47.695 degrees. An analogous calculation can be done to solve for theta 2, whose opposite side is the 6 centimeter, yielding this expression for the cosine of theta 2, which is numerically 0.8962, meaning that theta 2 itself is equal to 26.343 degrees. The final solution to this problem will be obtained by dealing with two magnetic field vectors. First, the magnetic field vector due to wire 1, B1, which will have both an x and a y component, and second, the magnetic field vector due to wire 2. In the drawing at the left, we have zoomed in on wire 1 so that we can make a simple drawing, confirming that the right-hand rule tells us that the magnetic field around wire 1 will be a circle, and since this wire has current coming perpendicular out of the screen, this means that the magnetic field at point P due to wire 1 is directed tangentially as compared to the circle, as shown by the green arrow. Noting that the angle theta 1 is located in this corner, we recognize that the magnetic field vector B1, when divided into components B1x and B1y, will form a triangle with the angle theta 1 in this corner. Therefore, B1's x component is positive, and it is the magnitude of B1, mu 0 I over 2 pi r1, the appropriate magnitude for a magnetic field due to a straight line of current, times the cosine of theta 1 to get the adjacent side. Similarly, we note that B1 has a y component. Its y component is positive, and we determine this y component by taking the magnitude of the magnetic field B1 and multiplying by the sine of theta 1. We are told in the problem that each wire carries a current of 35 amperes, and that the wire we're currently dealing with has a distance of 6 centimeters from that wire to the point P. Plugging in the actual numbers into both the x and the y components, we get the solutions. 7.853 10 to the minus 5 for the x component, and 8.628 times 10 to the minus 5 Tesla for the y component. We can then perform a rather similar calculation for the contribution due to wire number 2 that we'll refer to here as B2. Once again, the magnetic field due to the wire B2 will form a circle around the wire itself, and due to the fact that the current is coming out of the screen towards you, the magnetic field direction will be counterclockwise around that circle. We therefore recognize that at the point P, the magnetic field B2 is tangential to the circle and located as shown here. As in the previous problem, we recognize that the magnetic field in question will have two components. One is an x component, which is negative. The other is a y component. And we also recognize that the angle theta 2 in this corner is the same as the angle theta 2 in that corner. Following this, we simply solve for the two components. B2 has an x component, its x component is negative, and that x component will be the magnitude of B2 times the cosine of the angle theta 2. B2 has a y component, its y component is positive, and its y component is the magnitude of the magnetic field times the sine of the angle theta 2. Plugging in all the numbers and remembering that the angle theta 2 was 26.343 degrees, we get two results. Negative 6.273 10 to the minus Tesla for the x component, and positive 3.106 times 10 to the minus 5 Tesla for the y component. To get the total magnetic field, we simply add the x components to get the x component of our result, and add the y components of B1 and B2 to get the y component of our result. Maintaining our 10 to the minus 5 factor, we see that the x component of B total is 1.58 10 to the minus 5, and that the y component of B total is 11.734 10 to the minus 5. It is then very simple to solve for the magnitude of B total by taking the square root of B total x squared plus B total y squared. And when we do so, we get the final answer, 11.84 times 10 to the minus 5 Tesla. If we wanted to find the direction of this magnetic field, we would simply take the inverse tangent of the y component divided by the x component of the result. And since the x component of the result is positive, we would not need to add 180 degrees in order to get that direction vector.